Let's return now to translation heuristics. Specifically, how do we take a problem description and break it down in such a way that we can identify the simple events, the relationships to each other, and use that to figure out what rules to use. So I've got a little flow chart that you can use, do it over and over and over again, and so you end up with nothing but simple events. And that's certainly a systematic way to break that problem down, to translate it into a set of simples together with a set of rules that you should use in a particular order. So let's go through this. The first thing you always ask when you've got a probability problem is, what type of event am I trying to compute the probability for? If it's a simple event, then all I have to do is use the appropriate notion, the classical, the frequency, or the subjective interpretation, to estimate the probability of that event. If the principle of indifference holds, I can determine all of the favorable, all the possible outcomes. I'll use the classical. If I know the principle of indifference doesn't hold, but I do have time to make observations or have access to data, I can use the frequency interpretation. If I don't have either of those, then I'll have to use the subjective interpretation and use my knowledge of the world to estimate what I think the likelihood is and calculate it out in terms of fair betting odds. Suppose that my event isn't a simple event. Suppose I look at it and I go, okay, this has to be true and this has to be true in order for the event to occur. So I've got a conjunction. Then I need to ask myself, are those events independent? That is, does one happening affect the likelihood of the other? Or does one happening not affect the likelihood of the other? So if they're independent, then I can use that restricted conjunction rule. The probability of A and B equals the probability of A times the probability of B. Suppose I say, hey, wait a minute, no, these events aren't independent. One happening affects the likelihood of another happening. Eating a cookie affects the likelihood that someone else is going to eat that cookie. Well, then I have to use the general conjunction rule. The probability of A and B equals the probability of A times the probability of B, given that A has occurred. So when you go through and you start analyzing these problems, when you think to yourself, what has to happen for the event to occur? If you find yourself using and, if you say there's got to be this and that, then you know you've got a conjunction. But what if you don't have a conjunction? What if it's a disjunction? You say, okay, well, a favorable event could happen this way, or it could happen this way, or it could happen this way. If I know I have a disjunction, then I've got a question to ask, and that question is, are the disjunctive events exclusive? That is, can they both happen, or if one happens, the other doesn't? If they're exclusive events, then I can use that restricted disjunction rule. The probability of A or B equals the probability of A plus the probability of B. If they aren't exclusive, if it's possible for one disjunct to happen and the other, so that this disjunction could be true if one's true, or the other's true, or they're both true, then I need to use my general disjunction rule. And in fact, I can always use the general disjunction rule, though it can be more cumbersome. So I said the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. What if it's neither a simple event, nor a conjunction, nor a disjunction, but instead what I have is a probability, and now I've got new evidence, and I want to know how that evidence affects the probability? Well, then I'm going to use Bayes' theorem. So you can look at a problem and break it down this way over and over and over again until every event, every component of that problem is just a simple event that you've assigned a probability to. And that systematic way will help you to break down the problems in a way that allows you to solve them. Let's see how this flowchart would work on a basic problem. So we have a question that asks us, what's the probability of drawing 2 aces from a poker deck in 2 draws? The first version of that problem says, if the first card is drawn and replaced before the second draw. So I draw a card from the deck, say it's an ace, I then put it back into the deck, maybe shuffle the deck, and then I draw again. I have 4 aces, 52 cards in the first draw, 4 aces, 52 cards in the second draw. Now I really encourage people to stop the video when we start a problem like this, try and solve the problem, and then start the video and follow along with me and see how I did it and compare it to how you did it. So let's run through this. We say, okay, look, I have first draw, I have my second draw. I have to get an ace on my first draw, and I have to get an ace on my second draw. So I think to myself, hey, I'm going to need a conjunction rule. This is a conjunction, A and A, ace and ace. I have to get aces in both draws. So I ask myself that rule, is it independent? The answer for this problem is yes. All right. So I take out that card, I look at it, then I put it back in. I started with 52 cards, 4 aces. Now I've got 52 cards and 4 aces for my second draw. So they are independent of each other. So I know I can use that restricted conjunction rule. Now I've got to figure out, estimate the probability of drawing an ace from a deck of cards. There are 4 aces, there are 52 cards, so 1 out of 13 will be my likelihood. Since I replaced that card, that'll be the likelihood for both draws. So I can plug that into my equation, and now I get the probability of drawing an ace on the first draw and an ace on the second draw equals the probability of drawing an ace on the first draw times the probability of drawing an ace on the second draw. That equals 1 over 13 times 1 over 13, which equals 1 over 169. I could also do it in terms of decimals. 1 over 13 is approximately 0.077. So 0.077 times 0.077 equals approximately 0.0059. Let's do one more. What if, when I draw that first card, I don't put it back into the deck? So on my first draw, I've got 4 aces and 52 cards. On my second draw, I've got 3 aces and 51 cards. So again, I've got 2 draws. I have to get an ace on the first and an ace on the second. So I know I'm going to be using a conjunction rule. I ask that all-important question, are the 2 events independent? The answer this time is no. If I draw an ace on that first draw, then that changes the probability of drawing an ace on the second draw. There's 1 less ace and 1 less card. So now I know I've got to use the general conjunction rule. So now I'm going to have to estimate the probabilities for drawing an ace on the first draw and the probabilities for drawing an ace on the second draw. I plug those into my equation. The probability of drawing an ace on the first and an ace on the second draw is equal to the probability of drawing an ace on the first draw times the probability of drawing an ace on the second draw, given that I drew one on the first. Or 4 divided by 52 times 3 divided by 51, which equals 12 over 2,652. Or if I do it in decimals, 4 over 52 is 0.077 times 3 over 51 is 0.059 approximately, which equals 0.0045.